everyone. So continuing with the concept called as chemoselectivity. We have already seen in our previous classes how a chemoselectivity can be dictated upon. The plants, animals or microorganisms produce a number of chiral and achiral complicated structures. We already know that there may be number of chiral systems, there may be number of achiral systems which may be complicated to synthesize. Examples can be antibiotics, alcoholic system, alkaloid system, chlorophyll system, steroidal system, biopolymers, carbohydrates, fats, vitamins, dyes, etc. These all systems either have one of the system as a chiral system which needs a lot of preparation previously even before they are synthesized in the laboratory. Hence, the chemist determines the structures of these compounds and tries to synthesize them using a retrosynthetic approach. Generally, systems like alkaloid system, antibiotic systems, steroidal systems, they were first identified in a natural phenomena and then the chemist tries to do a retrosynthetic approach so that these compounds can be synthesized in the laboratory. Hence, to achieve these systems, there are two types of selectivity possible for any synthesis. Now, when we say selectivity, earlier we have started to understand about chemoselectivity. The other system can be Regio Selectivity. The third system can be stereoselectivity. The systems can be majorly which fall into trying to do a retrosynthetic analysis would be, first would be chemoselectivity. Chemoselectivity is nothing but it is to decide which group reacts, and regioselectivity is where the reaction takes place in that particular group. Obviously, we have already seen what is the type of stereoselectivity. Stereoselectivity is nothing but is how the group reacts with respect to the stereochemistry of the product. You have already seen in various instances the stereochemistry of various final products. But chemoselectivity is which group is going to react, the decision to be taken. Regioselectivity is where the group is going to go and react and what kind of a final product we are going to get, and where the reaction takes place in a particular functional group, that decision is called as regioselectivity. Selectivity can be attained by selecting appropriate starting materials, reagents, solvents, reaction conditions, and most importantly protecting and deprotecting methods. We have already seen in the peptide synthesis how important is the protection and deprotection step and also the activation step. Hence, in the same way, selectivity can also be achieved by choosing a proper starting material, proper reagents, solvents and the reaction conditions. What is a protecting group? It is entered into the molecule through chemical modification of a functional group for obtaining chemoselectivity in a chemical reaction. We have already seen what is a protective group. Now, for example, if there is a presence of NH2, if I just convert it into NHCOCH3, what I have done here is I have protected the NH2 group by converting it to its respective acetyl group, and hence in this way I have protected the NH2 group from an unnecessary reaction. Now, for example, certain functional groups and what are the type of their protective groups can be seen in this particular table. If there is a presence of an OH, it can be converted to a respective ester, it can be converted to respective ether or ether silyl system. For example, if there is a presence of an OH like this, it can be converted to an OCOCH3 which is an ester group. It can be converted to OCH3 which is an ether group, or it can be converted to OSI3 system which is a ether silyl system. So in this way, alcohol can be converted into various types of protecting groups. Amine system can be seen as substituted amine. Just now we have seen an acetyl group. It can be converted to an amide system, that is NH2 group can be converted to NHCO system. This is an amide system. It can be converted to an carbamide system. It can be converted to a sulfonamide system. Carboxylic group again can be observed as it can be converted to an ester system. If there is a presence of carboxylic group, it can get converted to an ester system. Or it can be an ester silyl system, that means introduction of a silyl group, or it can be converted to an oxazolene system. So these are some of the functional groups and the respective protecting groups. This you have also learnt in your previous semester. Now what are the functions of a protecting group? Protection of a sensitive functional group. It becomes possible to make reagents that would otherwise be unstable. If there is any type of reagent which is very unstable, protection of such reagent can be done by a protecting group. In turn, we can easily achieve the synthesis of that particular reagent. Protection also allows us to overcome simple problems of chemoselectivity, in the way that when we say chemoselectivity, we want to decide which group is going to react. In turn, if I have to choose which is the group that is going to react, I have to see that I should achieve a proper chemoselectivity. So to achieve a proper chemoselectivity, I might be able to do a first protection so that I can achieve a proper chemoselectivity and simple problems could be solved. The other important function of a protecting group is to stop the reagent from attacking itself. That means some of the reagents will do a self-attacking system, like for example when you do an aldol condensation or when you try to do a Cannizzarose reaction, there may be a self-condensation reaction. To avoid this, generally what we do is we try to do a protecting system. That means first the protecting group is introduced so that there is no attacking of the reagent on itself. Coming to the concept of chemoselectivity, it is helpful in the molecules which possesses more than one functional group. This we have already seen in the previous discussion. The selective reactivity of one functional group in the presence of others is controlled by chemoselectivity. That means I can control how only one functional group can react and the other functional group may not react at all. The chemoselectivity is supported by protection and deprotection. Definitely, if there is some kind of protection and further deprotection, it is always supporting the chemoselectivity process. Now, for example, when I want to do a selective reduction, the selection of a proper reagent plays an important role in chemoselectivity. We have already seen that a particular reagent plays a very important role. The selective reduction of either the double bond of the carbonyl group in cyclopentene pent-2-enone is a reagent specific. For the chemoselective reduction of C double bond C over C double bond O, bond is performed by catalytic hydrogenation. Now for example, let us observe this particular system. This is a cyclopentenone system. In the presence of hydrogen and palladium catalyst, only the C double bond C is reduced and the carbonyl carbon remain intact to give me cyclopentenone system. Now we can observe here that I am doing a chemoselective reaction by not allowing the carbonyl carbon to react, whereas only the C double bond C reacts, and I have chosen a proper reagent called as hydrogen and palladium catalyst. Now for example, in the same system, that is cyclopentenone system, I want to react the carbonyl carbon but I want to keep the C double bond C intact. Then what we can do? The reduction of a carbonyl carbon over C double bond C is performed by reducing agent sodium borohydride. So the reagent that we choose here would be sodium borohydride. The reaction of cyclopent-2-enone with sodium borohydride, it is going to give me cyclopentanol. In this case, only the carbonyl group is selectively reduced to OH group. Now can we not observe here that carbonyl carbon is reacting so that it is getting converted to an OH, whereas C double bond C has remained intact. This is because we have chosen the reagent called as sodium borohydride in the presence of cerium trichloride. So in this way, chemoselectivity helps, or it tries to make a bifurcation onto which particular group is going to react. The next example can be when there is a presence of alpha beta unsaturated esters in the presence of alkene system. Now can we not observe here that there is a presence of alpha beta unsaturated ester, which is the presence of an ester over here. The reduction of the compound with magnesium in the presence of methanol reduces the double bond present at the alpha beta position of the alpha beta unsaturated ester, giving the products. Now we can observe that if I have added magnesium in the presence of methanol, we can observe that only the alpha beta position have been reduced to get the final product. So in this way, chemoselectivity by choosing a proper reagent plays an important role as to which particular group gets to react to get the final product. This is the concept of chemoselectivity. Now coming to the concept called as regioselectivity. Now in regioselectivity we also have to understand that this is about giving the preference for bond making at a particular place when there is a possibility of bond formation of other possible positions also. If there are n number of possibilities present for the bond formation, which particular bond formation takes place gets to be decided by the concept called as regioselectivity. There is a preference of one reactive site with respect to other reactive site. Now we always understand that in a regioselectivity phenomena, there is always a preference given for one reactive site with respect to other reactive site. Now for example, we have already learnt about Markovnikov's rule and anti-Markovnikov's rule. If there is a particular reagent, now for example, if there is a starting material called as vinyl benzene, in the presence of just the HBr, it is going to give me 1-bromoethyl benzene. Or if there is a presence of HBr in the presence of per acid, then it is going to follow an anti-Markovnikov's rule to give me 2-bromoethyl benzene. Now we can observe here that because there is a presence of a per acid system, the preference of the reactive system completely changes, giving me a 2-bromoethyl benzene. Whereas if the per acid was not present, then we started getting 1-bromoethyl benzene. This is how a preference in the regioselectivity can be observed. Now this regioselectivity can be applied to a system called as Birch Reduction. What is Birch Reduction? Aromatic rings undergo a 1,4 reduction to provide unconjugated cyclohexadienes. Now this particular system is called as Birch Reduction. That means aromatic rings undergo 1,4 reduction to provide unconjugated cyclohexadienes. This reaction is performed by sodium or lithium metal in liquid ammonia and in the presence of alcohol. Here, the site of reduction is dependent upon the type of substitution present in the aromatic ring. Now we can say that Birch reduction is done in the presence of sodium or lithium in the presence of liquid ammonia. This is a very important named reactions where aromatic rings are undergoing a 1,4 reduction. But the reagents can be sodium or lithium in the presence of liquid ammonia. Now what is this Birch reduction dependent upon? Either it is dependent upon an electron donating system or it is dependent on an electron withdrawing system. Without any type of substitution, if I take a benzene in the presence of sodium in liquid ammonia and ethanol system, it is going to give me cyclohexadiene system. Now this is a Birch reduction which is going to give me just the system like 1,4 reduction to give me unconjugated cyclohexadiene system. Now we can observe in the final product these two double bonds are unconjugated system. Now in terms of regioselectivity, if there is a presence of electron donating group like methoxy system or if there is a presence of electron withdrawing group like a carbonyl group or a carboxylic group, now the preference is based on the mechanism of the reaction where the radical anion is protonated initially determines the structure of the product. While we try to perform the retrosynthetic analysis, these preferences play an important role in the synthetic design of any molecule. Now when I say regioselectivity, we try to design any type of synthesis, then we also have to pay attention towards whether the substitution on the benzene is electron donating system or whether it is an electron withdrawing system. Now for example, if I have a methoxybenzene, this in the presence of sodium and liquid ammonia in the presence of ethanol system, it is going to give me 1-methoxy cyclohexa 1,4-diene. Now for example, this is going to give me 1, 2, 3, 4. Now we can observe here that I am going to get an cyclohexa 1,4-diene system if there is a presence of a methoxy system, which is an electron donating system. If there is a presence of an electron withdrawing system, like for example carboxylic group, in Birch reduction in the presence of sodium and liquid ammonia in the presence of ethanol system, now this is going to give me cyclohexa 2,5-diene carboxylic acid. Now when I observe here, it is 1, 2, 3, 4, 5. So we are going to get a 2,5-diene carboxylic acid. If there is a presence of an electron donating system, we get an 1,4-diene system, and if there is a presence of an electron withdrawing system, then I am going to get a 2,5-diene system. This is how regioselectivity can be applied for a fewer named reactions like Markovnikov's rule, and we can also apply it for the Birch reduction. So basically regioselectivity decides on to which group reacts and what is the final group that we are going to get, or the final compound that we are going to get. Whereas chemoselectivity decides using a particular reagent how we can do a particular reaction and arrive at the final product. Thank you.